Hello everyone, it is the time of the year again. The IMO 2021 was held on 19th and 20th of July this year. The host country is Russia, and the participants once again took the exam in their respective home countries. Now there are some really insane problems on day 1, so without further ado, let us take a look at the problems for this year. Problem 1 is as follows. Let n greater than or equal to 100 be an integer. Ivan writes the numbers n plus 1 to 2n each on different cards. He then shuffles these n plus 1 cards and divides them into two piles. Prove that at least one of the piles contains two cards such that the sum of their numbers is a perfect square. Okay, before going into the solution, I'll give a bit of motivation because otherwise the solution will look really random. But the motivation is actually really natural and lends itself to the solution. So the way we'll reason the problem is wishful thinking. Well, if we can actually find three distinct numbers among the cards, such that their pairwise sum is a perfect square, then we will be done, because we can never divide the three cards away from each other when we divide them into two piles. So we'll do further wishful thinking. What if we can find some integer k such that the pairwise sum gives consecutive squares k minus 1 squared, k squared, and k plus 1 squared? Well, for this to work, we can be a little bit smarter about it. We notice that the sum of the left hand side is 2 times a plus b plus c, which is an even number. So if we want to have hope of this happening, we see that we cannot really put an even square plus odd square plus even square, because that will give an odd number. Instead, we will want an odd square plus even square plus odd square. So we'll write k as 2l, and it becomes our hope to find a, b, and c and some l such that this system of equation is true. Well, actually, we can also continue to be smart about this by saying let's choose l and then we solve for a, b, and c. So we can actually solve for a by summing the first two equations and subtracting the third, and then dividing by 2. So a can be given by this equals to 2l times l minus 2. Similarly, you can solve for b and solve for c. So actually, we have reduced our wishful thinking into a very clever question. Can we find l such that the numbers 2l, l minus 2 and 2l, l plus 2 lies in n to 2n? Because if that is the case, I can always define a to be this, b to be this, and c to be this. And notice, okay, a is less than b less than c by the way I set this up. But anyway, if I define a, b, c as follows, we have a plus b, a plus c, and b plus c equals to these squares. So then we can never split these three. We can always find two cards such that their sum of the numbers is a perfect square and they belong to the same pile. Okay, so let us now turn our attention to this problem instead. So we need to find L such that n is less than or equal to 2l, l minus 2, less than 2l, l plus 2, less than or equal to 2n. Well, to maximize our hope of this happening, let's first focus on the left side. There are many possible values of L that can be bigger than, that can cause this expression to be bigger than or equal to n. But if we want the right side to hold, our best chances is to choose a smallest possible L such that the first inequality holds. So we let L be the smallest integer such that n is less than or equal to 2l, l minus 2. So the first inequality holds. And let us cross our fingers and hope that we end up with the expression that this L actually satisfies the upper bound here. Okay, let's see whether that is the case. Now to prove that, we first observe that since L is the smallest integer such that this inequality holds, means that L minus 1 violates the lower bound. So we have n greater than 2l minus 1, l minus 3. So actually, if we can show that this further inequality holds, then n will be bigger than L plus 2. Then 2n will be bigger than 2L plus 2, which is exactly the upper bound inequality that we want to show. So we want to show this inequality, which we can just perform our usual basic algebra manipulation. We end up with this quadratic equation. Fortunately, or maybe unfortunately, we see that this quadratic holds for L greater than or equal to 10. We can prove this easily by substituting L equals 10 and show that the quadratic is bigger than 0, and this quadratic is increasing from L greater than or equal to 10. So, okay, we only managed to prove this for L greater than or equal to 10. Okay, it's actually not as bad as it seems. We notice that if n happens to be bigger than 126, then the minimum L such that this expression holds must be at least 10, because if we choose 9 instead, it will be 2 times 9 times 7 equals 126, but n is bigger than 126, so whatever minimum L satisfies this lower bound, L must be greater than or equal to 10. So if n bigger than 126, L will indeed be bigger than or equal to 10, and the problem is solved. But the question says n is bigger than or equal to 100. So what happens to the numbers from 100 to 126? Now do not worry, in this case, we can directly check that L equals to 9 works. Because 2 times 9 times 7, which is this expression here, and 2 times 9 times 11, which is this expression here, they are equal to 126 and 198, and both of them will definitely lie in n to 2n for these values of n. So we cover all the cases we need to check, and that's the end of problem 1. So an interesting problem, and if you look at the problem initially, you might think, oh, it's a number theory problem because it has perfect squares and deals with integers. And indeed, the problem selection committee classified this as a number theory problem. But actually, I think you might agree that this is more like an algebra problem. But anyway, that's all for question 1. Let us take a look at question 2. So for problem 2, we have an inequality problem. So this is similar to the case as last year, where problem 2 is an inequality problem. So we are supposed to show that the double sum of square root mod xi minus xj is less than or equal to double sum square root mod xi plus xj, and so that this holds for all choices of x1 to xn. So a very succinct problem, but it turns out that this problem is really quite a monster. You will see why after we go through the solution. Just to caveat first that there will be a section in the solution that I'm showing that involves a bit of deeper mathematics, but I'll make a comment at the end on why I think this is really not really escapable, and there are actually many comments on the forum that talk about how this problem is more suitable as an undergraduate mathematics competition problem, and you'll see why after we go over this solution. So anyway, the way we will prove this problem is to prove by induction on n. Now the base cases n equals 0 and 1 are trivial, and I'll leave it to the viewer as an exercise to check this. So for the induction, we'll assume that the cases with n minus 2 variables and n minus 1 variables are proven, and we will now work on the case with n variables. So keep this at the back of your mind. The key observation is to consider what happens if we shift all the variables by a constant k. Now, the left-hand side, being absolute value of the difference, will actually not change with this shift. So the left-hand side stays the same. But the right-hand side has an additional 2k that will appear here. So shifting all the variables keep the left-hand side fixed but changes the right-hand side. So naturally, you'll want to consider what happens if I just shift everything so that the right-hand side achieves a global minimum, and I just need to prove the inequality for that special case. So good idea. Let us let k star be any real number such that the right-hand side attains a global minimum. Now, if you are wondering in your mind, how do we know that such a k star exists? Congratulations, because you have a really rigorous mind. And indeed, this is the part, this small section requires a bit of a deeper mathematical thought. So actually such a k star exists because if k goes to infinity or minus infinity, this expression here, this function, will eventually become increasing. So in between that portion where it's eventually increasing, there must be some value of k star that causes it to achieve a minimum. Well, not exactly. There's one more subtlety. Actually, you need also the ingredient that this function is a continuous function in k. So with that, the two ends increasing and then in between is a continuous function. With it makes intuitive sense that there will be a k star that achieves a global minimum. To show this rigorously, you will need some undergraduate mathematics, which I will not go into. So anyway, let's just move on with this. Suppose that we believe that there's such a k star where right hand side attains a global minimum. Then as we explain, what we'll do is it suffices to prove the inequality holds after we make the replacement xi shifted by k star. So from this point, we assume that we have already made this replacement. Now, having made the replacement, the right hand side is now at a global minimum with respect to any shift. I claim that there exist two indices, not necessarily distinct, such that xk plus xl is equal to 0. Now, the proof is by contradiction. Assume that's not the case, then xi plus xj is not equal to 0 for all I and j. This means that there exists some sufficiently small positive constant, epsilon, such that for every choice of I and j, xi plus xj, as well as the version shifted by minus 2 epsilon and the version shifted by 2 epsilon, will be all of the same sign. 1 epsilon is chosen for all choices of I and j. But each choice of I and j will have could be plus plus plus, and another choice of I and j could be minus minus minus. In any case, for each choice of I and j, we can then apply Jensen's inequality on the concave function square root of absolute value of x. So we get this inequality here. And because it holds for each choice of I and j, we can sum over all choices and get this double sum is less than twice of this double sum. Okay, I'm just going to break up the double sum to make the next point clearer. So we have this, and from here it is clear that either this double sum will be less than this double sum, or this double sum will be less than this double sum. And what this means is that it's technically possible to shift all the terms, the xi's, by either epsilon or minus epsilon, and it will further reduce the right hand side. And this is a contradiction because we are at a global minimum with respect to any shifts. So the claim is proven, and it's only a tiny bit more before we finish the proof. Now, we need to consider two cases. The first is if k equals to L. In other words, xk plus xk equals 0, so there exists k such that xk equals 0. We can check that on the left hand side and right hand side, the sum of terms involving xk are equal. I'll leave the viewer to work out the details, but roughly speaking, for example, general index I here and the index k here, this will be square root of xi minus 0. Whereas on the other side is square root of xi plus 0. So we can cancel out the general index I paired with a k on both sides. So I'll let the viewer to work through, but this is quite straightforward. So we can actually remove the consideration of xk from the entire inequality and reduce the number of terms to n minus 1. The other case is that exists k not equals to L such that xk equals to minus xl. Now this is going to be similar to the previous case, but it's a bit more tricky. This time, the viewer can check that the terms involving xk on one side can be paired with terms involving xl on the other side. Or rather, terms involving sk or xl can be paired up between the left and right side such that the sum of the terms on both sides are equal to each other. For example, I just give one illustration. We take a general index I here, and for j we fix it at k. We get xi minus xk. I pair that with a general index I, and for j I take it to be L, then I get xi plus xl, right? And xk equals minus xl, so actually the xi minus xk here is the same as the xi plus xl here. So we can do this pairing. I'll let the reader check through more carefully, and then we can remove the consideration of xk and xl from the inequality and reduce the number of variables to n minus 2. So by induction, we are complete. So that's all for problem 2. It's really insane problem. And you might ask, well, there's one part in the middle where we use a bit of undergraduate mathematics to make it completely rigorous. So this proof is completely rigorous, just that the existence of K star involves undergraduate math knowledge. So is this really necessary? Well, I came across some proofs on forums that are similar. Now, I do not mean to be condescending to the poster of this solution and so on, but I just want to give a quick explanation on why some of the other proofs also seem to sidestep this need for undergraduate mathematics, but actually there are some gaps, and filling the gaps end up introducing back like deeper mathematics. So for example, in this proof, right, the way it proceeds is that it's similar idea. So we say that, okay, this time I start from claiming that if xi plus x0 is not 0, xi plus xj is not 0 for all ij, then I can shift by some amount and reduce the right hand side. And the proof is similar. We use the Jensen inequality and so on. So from here, it shows that, okay, I can, if xi plus xj is not equal to 0, I can always find some shift that reduce it. And therefore, we reduce the problem to the case where xi plus xj equals 0 for some ij. The big question mark is, this therefore has a lot of subtleties hidden in it. And what do I mean? Let me give you a very simple illustration. Let's look at this function here. For this function, it's very clear that if I start anywhere, I can always shift by epsilon in some direction and the function value reduces. But it doesn't mean that therefore my minimum case that I need to be considered is given by this value. It's not, right? Because yeah, indeed, I can always keep shifting by epsilon. Even when I'm very close, I can find some epsilon that still further reduces my value. But hey, actually, it doesn't mean that at the case where shifting doesn't occur, my value is lower than what I can achieve from the rest of the branch of the function. So there's some subtlety here. Of course, you will realize that in our case, the key is that there's continuity of the function. So this dot cannot suddenly jump up here. The function, as you shift, it must eventually attain this value instead of suddenly jumping up. So continuity is used, and then that goes back to basically sort of the kind of rigor that we are trying to do in our proof. So anyway, if all this doesn't quite make sense, do not worry. These are just really some subtle points in the proofs that are found in other places. And one way or another, I think there's really no way to avoid a very much deeper mathematical understanding of how functions work, and some level of maturity will be needed for a completely rigorous proof. Okay, that's all I want to say about problem 2. Let us take a look at problem 3. Okay, so for problem 3, we have a geometry problem. And when you see geometry for problem 3, you know that there is some very deep stuff going on here. And actually, this is a very beautiful problem, but indeed, being a problem 3, the solution is quite long. There are many steps, and there's some quite involved tools that are being used here. So let's take a look at what this problem says. Let D be an interior point of the acute triangle ABC with AB longer than AC. So that DAB equals CAD, meaning basically D lies on the angle bisector of angle A. Okay, the point E on the segment AC satisfy the blue angle ADE equals the other blue angle DCB. And the point F on segment AB satisfy the right angle FDA equals the other right angle CBD. And the point X on the line AC satisfy CX equals BX. Okay, and then we let O1 be the circumcenter of triangle ADC, and then we let O2 be the circumcenter of triangle EXD. And the question is to prove that BCFE and O1, O2 are concurrent. The way we'll actually prove it is to let P be the intersection of BC and FE, and then the whole point is we want to show that P lies on O1, O2. So that's the approach we'll take. Now there are many steps to this problem. Let's take it step by step. First step is to prove that BCEF are concyclic. Now before doing that, I need to introduce the concept of an isogonal conjugate. So the way this works is as follows. We have a triangle and then there's a point P. So I want to construct this thing called the isogonal conjugate of P, which is the point P star. So from P, we have the lines AP, BP, and CP, correct? What we do is we take AP, we reflect about the angle bisector A, and we get the red line. Similarly, we have BP, we reflect about the angle bisector of angle B, we get the red line. And CP, we reflect about the angle bisector of angle C, and we get the red line. I claim that actually the three red lines will intersect at a point, and this point is called the isogonal conjugate of P. Now the red lines are concurrent by the trigonometric version of Siva's theorem. So if you have not heard of this before, do check it out. It's quite cool. Basically, instead of like the ratios of length, we have ratio of sine this angle over sine that angle times sine this angle over sine of that angle times sine this angle over sine of that angle is equal to 1. So go check it out. It will be very straightforward why the red lines are concurrent. Okay, so the way to prove that BCEF are concyclic is to first introduce the isogonal conjugate of D in triangle ABC. So notice that because D lie on angle bisector of A, D prime will also lie on the angle bisector of A. Now in this diagram, I showed D prime to be below D, but a completely analogous proof will work if D prime lies above of D. Now by definition of isogonal conjugate, FBD prime will be the same angle as CBD prime, because basically we reflected the line BD about the angle bisector of B. So FBD prime equals the right angle, which equals this right angle. This shows that FDD prime B is concyclic because this internal right angle here is equal to the opposite extended right angle. Similarly, EDD prime C will be concyclic. This means that AF times AB equals AD times AD prime. And similarly, AD times AD prime equals AE times AC. So we have AF times AB equals AE times AC, which shows that BCEF are concyclic. Okay, I'm going to park this fact into my little parking lot over here. Okay, the next thing is to do some angle chasing. Okay, firstly, I'm going to show that the gray angles are equal. Well, that's quite straightforward because we have BCEF is concyclic, right? So this gray angle is equal to this gray angle. Okay, and then I'm going to show that the purple angles, three purple angles are equal. Well, indeed, firstly, this purple angle is opposite this, right? So this is equal to this purple angle. Now, this purple angle is 180 degrees minus gray minus half of angle A. Remember this angle bisector, so half of angle A. On the other hand, this other purple angle is equal to 180 degrees minus this gray angle minus this angle, which is also half of angle A. So indeed, this purple and this purple are equal. So all the purple angles shown are equal to each other. Okay. So what does this tell us? This tells us that actually angle EDC, which is what we are ultimately interested in, this green angle EDC. Well, firstly, we have that is equal to 180 degrees minus the blue angle here, minus this unlabeled angle. Now this is also blue, right? So 180 minus unlabeled minus blue is equal to this DZC. So the green angle is also equal to angle DZC. Now angle DZC is equal to these opposite two angles of the triangle. So it's equal to angle the red angle plus BDZ. And we have just shown that this angle, so this angle here, BDZ, is 180 minus red minus purple, which is the same as DFY, so this angle over here. So ultimately, what I have just shown is that this green angle is equal to this red angle plus this orange angle here. This is really what we want from this angle chasing step. And why is this important? Well, it shows that we can actually construct we can actually cut this angle into two parts with a line segment. Let's call the line segment dp prime, so that we have this part is equal to orange and this part is equal to the red angle. So because we know that this angle is orange plus red, so we can always cut it in this way, orange and red. And we have this line segment, and we might ask, what is so special about this line segment? Well, if this is orange and this is orange, it shows that the line segment dp prime is tangent to the circumcircle of DEF. And at the same time, because this is red and this is red, it shows that the line segment is tangent to the circumcircle of BDC. And because it is tangent to both circles, it is the radical axis of the two circles. And the key point is to realize that we have other radical axes on this diagram. We have FE is the radical axis of DF, since F and E lies on the circle, right? So FE, or rather FE lies on the circle DF and it lies on the circle BFEC. So FE is the radical axis of those two circles I just mentioned. At the same time, BC lies on the circle BDC, obviously, and BC lies on the circle BFEC. So BC is the radical axis of the two circles I just mentioned. And we have this pairwise comparison of three circles. So by the radical axis theorem, the three radical axes will be concurrent. So what does that mean? It means dp prime actually passes through P. So I'm going to discard P prime and rewrite as dp is actually the line that is tangent to circle DF and circle BDC. And why is this important? It tells us that PD square is equals to PE times PF, and PD square is equals to PC times PD. So after this whole long sequence of reasoning, ultimately this is what we get. This is what I will park into my parking lot over here. Okay, step 2 done. Step 3, I'm going to construct a point M. Now this M is going to be the intersection of the circle AEF as well as the circle ECP. So the two circumcircles intersect at some point, I'm going to call that M. And let's do some angle chasing again. Now, what is this special about this point M? We have AME. Because the 4 points here are concyclic, AME is equals to BFE. And because again BFEC concyclic, BFE is equal to ECP. Now because these 4 points are concyclic, ECP is equals to 180 minus EMP. And what does this give us? This gives us that actually A, M, and P are collinear. So very interesting observation. We define this M and then AMP turns out to be collinear. And why is this important? Because it lets us now use the power of a point thing again. We have PE times PF equals to PM times PA. And okay, PE times PF is here. So I'm going to add this observation again to our parking lot. So we have a lot of equalities here, very interesting. And furthermore, this M is going to make B, E, M, X concyclic. So another concyclic quadrilateral. Okay, let us prove this with some more angle tracing. Now, BME is given by purple minus red. Now I'm going to show that this purple angle here is obviously equal to this purple angle because this is concyclic. Why is this concyclic? I mean by construction of M, right? This lies on the circumcircle. So this purple is equal to this purple. Now, this red, why is AMCB concyclic? AMCB is concyclic because look at this power of point. PMPA equals PCPB. So AMCB is concyclic. So this red is equals to this red. And FECB concyclic, right? So this red equals to this red. So now we have purple equals to 180 minus red. Substitute that back into the first equation. BME is 180 degrees minus 2 times red. What is 2 times red is this red and this red because XB equals XC, right? So this red and this red are the same. So 180 minus 2 red is actually BXE. So this angle equals this angle. Therefore, BEMX are concyclic. Okay, another fact added to our parking lot. Now, we are not done, but we are getting close. Almost the final step. Now we define K to be the intersection of BM and AC, and then T is the intersection of the other intersection of the blue circles. Okay. Now we can see that actually BCMA is concyclic, right? We have that because BCMA is concyclic. Yes, because of this power of pointing. PMPA equals PBPC, right? So BCMA concyclic. Now we consider power with respect to K. This gives us BK times KM equals CK times KA. Okay. We also know that BEMX is concyclic. This is what we just proven. So power of point with respect to K give us BK times KM equals XK times KE. Okay. So because these two are equal, we have XK times KA equals CK times KA equals XK times KE. So CK times KA equals XK times KE. Okay. Now, what does this tell us? So we actually realize that the power of the point K with respect to the first blue circle is equals to the power with respect to K, power of the point K with respect to the second blue circle. This means that K have equal powers with respect to the two circles, i.e. K lies on the radical axis of the two circles, which is dt. So K lies on the line dt, and this gives us that CK times KA is actually equals to all the powers with respect to K is equal to dk times kt. Now we know this is a straight line, we can use the power again, find the power. The power is equals to all the powers with respect to K of the two circles. They are all the same things. And this is equal to BK times KM, which is the original numerical value here. So anyway, we have all these equalities. And looking at the last equality, it tells us that BDMT, okay, that's a lot of letters, BDMT, they are concyclic. And this is the very last fact we need. BDMT is concyclic. Okay, we are very near the end now. And for the very last final blow, we need to use inversion. Yes, what is a problem tree geometry problem without inversion? So a very quick recap, inversion involves choosing a center and a radius r. And what happens is we have the point P will go to the point P prime such that OP times OP prime equals R squared, and P prime will go to P. So I assume you are familiar with some basic facts about inversion, such as a circle not intersecting O will be inverted to another circle not intersecting O, and so on. So we have all these equalities here. It's natural to consider the inversion about the center P and radius PD. Why? Because then B will be inverted to C, A will be inverted to M, and yes, and D stays as itself. So basically, the circle that passes through BDM will pass through the circle that passes through, will become the circle that passes through ADC. Now notice that T lies on both circles. This is from BDMT concyclic. And obviously, ADC is our other blue circle here. By definition, T lies on the blue circle because it's the intersection of the two blue circles. So T lies on both circles that invert onto each other. This means that T is a fixed point under the inversion. The other fixed point being being D. So if it's a fixed point under the inversion of radius PD, it means that PT equals to PD. And so PD equals PT, very good. P lies on the perpendicular bisector of BD. DT, too many letters. In other words, P lies on O1, O2 because O1, O2 is the perpendicular bisector of DT. Alright, okay, that is the end of problem 3. So, too many letters. My wrapping skills is not that good, but a really complicated geometry problem, but there's a lot of beautiful ideas involved. So hope you enjoy that solution. Let us talk a little bit about the statistics. So yeah, these statistics looks a bit funny because problem 2 is usually not that crazily hard, but this year problem 2 has 522 people with score 0, more than problem 3, and the average is actually very close to problem 3. Thankfully, it's still slightly higher than problem 3. Well, okay, slightly, but it's indeed a killer problem 2 that we have this year. So what do you think of this year's IMO problems on day 1? Let us know in the comment section below, and I'll be covering the day 2 problems in about a week's time. So please subscribe to the channel and turn on the notification bell to be notified when the problems for day 2 are up. So see you soon.